Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have seen so far are Markovian queuing models, which are basically nothing but queuing systems modeled by a continuous time Markov chain. We have seen that there is enough of such models itself to actually model many of the realistic systems in a more realistic manner, especially when you generalize to say a phase type distribution or something like that, okay, and all features can also be studied. But still, whatever it is the case that they are can be viewed as if they are the special cases of some Markov processes, analysis of some Markov processes, though the analysis that we carry out are in the context of queuing systems, okay. So that's what we have seen so far, whether it is BDP based queuing models or a more general Markovian queuing models or Markovian network based models. All these models are all basically built on or based on the Markov processes or Markov chains, especially the CTMC, except the discrete time model was basically the DTMC model. Now then all the theory that you developed in Markov chain were basically used to study this, okay. But now what we are going to do is that we are going to go a little bit beyond purely Markovian models to what are we call as semi-Markovian models, where we still retain some amount of Markov property there in the whole process, but it is not that a fully Markov process. So, we will see, as we go along, like you will understand what does this exactly mean. Now, to understand that, we need to extend our knowledge of Markov process to beyond something what is called as semi-Markov processes, okay. Now, that is what we are going to do as a stepping stone, like what basically we define or we consider for our analysis are what are called as renewal processes, okay. And these renewal processes in fact played a role in proving certain results of Markov process as well. Say for example, you have seen that whenever the stationary distribution exists, right, the probability that you find the system state is n is 1 over the mean recurrent time, right, the mean recurrence time is what then you have. So, that result basically follows immediately from a results from this renewal processes, okay. So, like that you could, there are some books like Ross for example, they first treat renewal process, then they come to Markov process, so that the proofs becomes easier and so on. So this also is an important process, but in our context also, like this is an important process with respect to queuing models in the way of generalizing our queuing models from the Markovian queuing models to something more general. So, we will just give some definitions and some basic ideas about these processes before we actually jump into the semi-Markovian queues, okay. Let us start with what we call as renewal process. What is a renewal process? It is basically we are first defining it before we look at anything else. So, this is what is the definition, that what you have here is a sequence of non-negative IID random variables with distribution function or the CDF is given by f, and we also assume that this has a finite mean mu. Of course, one can define more generality, but of course, we will assume that this is what is the setup that we have. Now, once we are given these xn's which are IID non-negative random variables, now you define, in fact, one can strictly say it is a positive random variables, what does it matter? Now, you define the sequence Sn, another sequence Sn by this, what is that? S naught equal to 0, Sn is equal to Sn minus 1 plus Xn, which is nothing but x1 plus x2 plus x2, x3 plus and so on plus xn for all n greater than or equal to 1. That is what you are defining this process Sn. Now, this is Sn is what we call it as the nth renewal time, while the time duration xn, because xn is what we are adding to the previous one, right, Sn minus 1 plus xn. So, S1 is basically S0 plus x1 and so on. So, this time duration xn, which is nothing but Sn minus 1 is what you call it as xn, is the nth renewal interval. Okay. So, this is what you have. So, you have the xn's which are basically the nth renewal intervals, and Sn you define based upon xn, which is the renewal time. Now you define a random variable which counts the number of renewals until time t by this quantity, which is n of t is maximum of n such that Sn less than or equal to t, right. That is what is the counting process. So, this is basically a counting process which is what counts the number of renewals until time t or up to time t. Then we call this continuous time process n of t for t greater than or equal to 0 as a renewal process with distribution f, or more often a renewal process generated by the distribution f, or a renewal process induced by the distribution f. Okay. So, this is what is called the renewal process, because here the interest is mainly in the number of events that is happening. You can think, you can associate this with number of a certain kind of event happening, okay. And this xn is basically, you can think of it as if the time between the consecutive events is what this xn's denote, and this Sn will give you the time of the nth event, okay. And this n of t would define the number of events happened by that time. Now, you can associate, for example, with respect to our queuing model itself, if you think of as an arrival, okay. If you think of as an arrival, that xn is the inter-arrival time, Sn is the time for the nth arrival, and n of t is the number of arrivals by time t is what then you can think, okay. So, in general, the word which is used is this renewals, okay. We may also say that xn defines a renewal process, and some authors also say that xn itself, xn is the renewal process, because in this definition you know that once xn are specified, then Sn is the sum of this, and then n of t you are defining in terms of Sn, which is basically in terms of xn, okay. So, one can define this process nt as a derivation of that. So, xn itself one can call it as a renewal process. So, what we have here, suppose if you look at the timeline here, so this is 0, okay. So, this is time, I can call this as S1, this is S2, this is S3, this is S4 and so on. Then this interval is basically what X1, this is X2 and this is X3 and this is X4 and so on, okay. So, that is what you have here. Now, right, you see here, this is what is the given x1, x2, x3, x4, which are all IID and positive. S1, S2, S3, S4 are the partial sums of this sequence, you can say. Then n of t is basically Sn less supremum of n such that Sn less than or equal to t. Suppose if I pick a t here, say for example here, Okay. Suppose if my t is somewhere here, suppose if I call this as my t, then n of t is here. Suppose if my t is here, then the maximum of this set, right, this set n such that Sn less than or equal to t is 0, it is empty set. So, the supremum of that is 0 with the convention that we follow. So, n of t is 0. So, you will get if t is here, it is 0. If t is here, then you can see the maximum of n, see this is S1 less than or equal to t is satisfied. So, the set is non-empty and n is 1, but n2 is not there. So, it is only 1. So, n of t is equal to 1. So, here n of t equal to 2, right, because for S1 also this will be true, and for S2 also this will be true, for S3 this will not be true. So, and hence my n of t is equal to 2 in this interval, right, for any t in this interval. Now, in this interval, suppose since I am taking this t here, so my n of t, if I write, it is basically maximum of 1, 2, 3, right. So, you can, if you want to include 0, you can include 0, no problem. Otherwise, you can see this thing here. So, this is 3 is what then you will get here, right. For any t in this interval, right, my n of t will be maximum of n's. So, n is 1, 2, 3, right. So, this is 3 is what. So, basically this gives you the counts the number of renewals that have happened by time t. See, this is what is the number of renewals have happened, because the fourth renewal happens, or the fourth arrival happens after time t, which is what you have taken as the this point here, right. So, this is what is the renewal process, right. So, this is what is, again you can think about it, right. Now, you can correlate this with your Poisson process easily, because if I take my xi's to be IID exponential, then this is nothing but your Poisson process, okay. Rather than taking any non-negative IID with distribution function f, if I take an exponential, then what you are going to get, or what you have got, is basically the Poisson process. So, this is in a way generalization of this Poisson process. By removing that, we will just see that now, okay. Now, if Sn equal to t for some n, then a renewal is said to occur at time t, and hence Sn gives the time or epoch of the nth renewal, and is called the renewal epoch or regeneration epoch, mainly renewal epoch, regeneration because of some other reason, but meant called so, which we will see little later. We will see why this word is also used. So, this n of t gives the number of renewals occurring in 0 to t. Okay. This xn is the inter-event time or waiting time between the n minus 1th and nth renewal. So, these are IID, that is what we have seen. Now, the Poisson process is the unique renewal process with Markov property, because we have seen from this kind of picture we have drawn for Markov Poisson process as well. You can see that you can easily relate it. So, this generalization of Poisson process, what do we mean? That the renewal process is a generalization of the Poisson process, and the renewal process is obtained if you remove the restriction of exponentially distributed holding times, and by considering that the inter-event times are any general IID non-negative random variables. If you consider so, then what you get is renewal. So, between Poisson process and renewal process, this is the difference that you have here. Okay. So, any example that we have considered so far, okay, Poisson process, arrivals happens, departure happens, right. Wherever you got this exponential, if you remove that exponential assumption and you replace with any IID positive random variable with a distribution function f and mean mu, then what you are going to get is a renewal process. That is the model that we have it in mind, okay, right. So, for example, consider an industrial process stage where production of a certain components are happening. After each batch, another batch is undertaken. Suppose the time taken to produce the successive batches, right, the time it takes to produce successive batches. If our IID random variable with distribution f, then we get a renewal process with distribution f. If you take arrivals, right, the inter event types arrivals, if it is the case, then you can think of that as in the arrival context, in the queuing context, that as a renewal process. If you take the service process, the duration of the service or service times are all any positive IID random variable, then the service process is the renewal process. Any other process that we have considered, be it working vacation or anything, that wherever exponential is there, if you can replace this, then what you get is the corresponding renewal process models. Of course, one has to look at how one can analyze such models. That will come a bit later, but as a way of generalizing the model, if you can think of a Markovian model where the Poisson process or exponential distribution is there, if you replace with, then what you get is the corresponding renewal processes. Okay, that's the way. How to handle such a process, how to analyze such a process, that's another question that we have to look at it. Okay. We will always assume that this is 0 for all n's. So, that's basically mean it is a positive random variables with no mass at 0 or any, means it is a continuous derivative. Okay. So, the strong law of large numbers implies in this scenario that Sn by n would tends to mu, which is what is the finite mean of this random variable x that we have considered almost surely sense, and hence this Sn would be less than t, right. It cannot hold for infinitely many n, and thus your n of t is finite with probability 1. So, n of t is finite with probability 1 is what, how you will see is that is basically it follows from the law of large numbers case that you have. So, probability of n of t is less than infinity is 1, that is what we are saying it here because of this reasoning. Now, we have the distribution function of Sn. So, Xn, the inter event times Xn, we assume that it has a distribution function capital F. Now, Sn, which is sum of Xn's, Xn's are IID. So, this Sn is basically the distribution function, if we call it this as f suffix n of x, is basically the probability of Sn less than or equal to x, right, time for the nth renewal. The distribution function of it will be given by this notation, this f n star of x. So, we will follow this f n star, of course, different way it is written with bracket n or star with bracket n, whichever way it is, like this means what it means is the n-fold convolution of f with itself. Okay. We have seen this follows. So, this one, because this is x1 plus x2 plus x3 plus xn less than or equal to x, where xn's are IID. Okay. So, that is given by the convolution. How it follows? It follows from this fact. Now, you take these two random variables x and y, which are independent but distributed according to f and g respectively, right. It has different distribution function. Just for the sake of consideration, you consider that these are f and g. Then we know that probability of x plus y less than or equal to t is what is given by the convolution of f and g, which is basically in continuous, for continuous random variables it is this. In discrete random variables, it is summation, say p and r is the are the the PMFs of these random variables, then we know P of n minus I and R of I is what is the quantity that you will have, which is exactly the same thing in this particular case with respect to the distribution function which you write. This is what we call it as the convolution. Now, what is this? This is n-fold convolution, right. This is two-fold in a way. So, this n-fold convolution is what then you get. Of course, if you are working in transform domain, you know that in this particular case, this is nothing but the nth power of the transform of the random variables xi's, right. But when you are working in the time domain, this will become the n-fold convolution, that is what it is, right. So, now it can be shown that this one, which is exactly similar to Poisson process case as well, that this holds with probability 1, okay. Therefore, the quantity 1 by mu, right, here you have to be careful, this mu is different from Poisson process lambda or mu that we have used. This is 1 over mu, this 1 over mu, which is basically the inverse of the mean length of the renewal interval, is called the rate of the renewal process. If you want to call say something as rate of the renewal process, much like the case that you had for in the case of Poisson process, then you would call this 1 by mu, where mu is the mean of the inter event times or inter renewal times. So, that is 1 over mu is what you call it the rate of the renewal process, right. So, what we have to remember is the distribution function of this Fn, which is basically Sn, is basically given by the n-fold convolution of the distribution function of x, because xn's are IIDs. Okay. Now, in the study of renewal processes, the renewal function and renewal equation are the most important quantities of interest. Okay. So, that is what we are going to construct, and we will see like what is that and so on. Okay. Now, observe that this event, what is this event? This is the event that n of t is greater than or equal to n, means the number of events, right, in time interval 0 to t is at least n. It is equivalent to Sn less than or equal to t. So, this is n of t is greater than or equal to n is same as the nth renewal is before time t, then only n of t will be at least n, right, unless this is there. So, you can go back here and see your diagram that what is n of t here and then what it should be having here. This is the equivalent events, or equivalently you can write the converse of this event to be this complementary events as this. Now, we want to know the distribution of this n of t, much like in Poisson process we have obtained the distribution of the number of events in 0 to t. So, here number of renewals in 0 to t, which is what we want to obtain. Now, how do we get? So, that is if you call this as p of t, okay, so this must be capital P. Okay. So, this is probability of n of t equal to n. You can write that as probability of n of t greater than or equal to n minus n of t greater than or equal to n plus 1, right. So, that is what is the case here. You know from the distribution function, the way you define the distribution function. But this event is same as this event and this event is same as this event. So, and hence you can write this as probability of Sn less than or equal to t minus probability of Sn plus 1 less than or equal to t. But this is we have already seen, this is nothing but Fn of t minus this quantity is Fn plus 1 of t. But this is the n-fold convolution of f with itself, right. With itself means in this case f with itself means f star f of t, that is what you mean to say, right. So, this means that f n star of t minus f n plus 1 star of t is what we are obtaining it as. So, in terms of the given distribution function f given in terms of the n-fold convolution n plus 1 convolution, then we can define what is this quantity. Now, this function m of t, which is expectation of n of t, is what is called the renewal function of the renewal process with distribution function f. So, the mean of this renewal process, the mean process in a right, it's not process because there is no randomness here, but it's simply a function of t. So, this is what is called the renewal function of the renewal process with distribution f. Now, this renewal function, as we just said, plays a important role in the analysis of renewal processes. And here, so the expected number of renewals in 0 to t, which is m of t, is then once I know this Pn of t, then it is basically it's the mean is given by this, where my Pn of t, since we already obtained to be in terms of the convolution of this f, so that I can substitute here. Now, if I expand this n times Fn star minus n times n plus 1 star, if I expand this, then I will be obtaining this quantity here, right. So, you just have to n times this with the previous one and so on. If you just expand it, you will arrive at this expression, which is basically summation of f n star of t. Now, what I can do? I can take out the first term from here out. So, that is basically f1 star, which is f1 star is simply f of t, right, plus summation 2 onwards, which is again I rechange the index from 1 to infinity, write that as f of n plus 1 star of t, n plus 1 fold convolution. Now, I consider this quantity, the second term in this renewal function, which is this, right. Now, f n plus 1 star, you can write it as a convolution of f n star and f, right, and that is precisely what we have written here, that it is 0 to t f n star of t minus x d f of x. Okay. Now, assuming that you can interchange this integral and sum, assuming that all the condition that is required for it valid. So, I can interchange these two to get this, but then now this quantity I know it is nothing but m of t minus x, right, because my m of t is this quantity, right. So, this is m of t minus x. Now, if I substitute this as m of t minus x and put this expression in for the second term, I will get this equation, right. I will get this equation, and this is the most important equation in renewal theory, which is called as renewal equation. So, renewal equation is nothing but the integral equation. You see here, this is an integral equation because m of t is the one which you need to determine, and this m of t appears inside this integral, right, and also outside. So, this is a integral equation, right. So, this is the integral equation satisfied by the renewal function, is what is called as the renewal equation or the fundamental equation of renewal theory. Now, in the study of renewal process, the major portion is concerned with what is the properties of this m of t, and from there what is the inference that you can give with respect to the renewal process and so on. Okay. So, the results that are connected to that are what are called as renewal theorems, which are basically elementary renewal theorem, Blackwell's theorem, key renewal theorem and so on, which basically involve the limiting behavior of m of t, which are all powerful results in renewal theory, and from the applications point of view, that is what is most relevant, and you can refer to RAS or any standard text for what are these results and what are their implications and so on. Of course, we require that much, so we just aren't going to details, and also for lack of time. Okay. For interested people, you can always refer to this. Okay. So, the renewal function means this quantity, and the renewal function satisfies this renewal equation. So, once I have this renewal equation, of course, you can write the solution of this also. The solution will be in terms of again renewal function and so on. So, that is a different matter. Now, the two quantities here which is of interest and which will be have to be handled carefully in comparison to our earlier models are what are called as residual lifetimes and excess lifetimes. Okay. So, basically what we have two random variables of interest, we will define one by one. So, how do we set? The setting is that for any given t strictly greater than 0, so there corresponds a unique n of t such that this is happening, right. So, t falls in between some n of t for some n, and s n plus n of t less than or equal to t strictly less than s of n of t plus 1. That is, t falls in the interval x n t plus 1, like you can recall the what we have beginning in the description that we have made. Okay. So, t falls in exactly one of these intervals for any t, right. Then the residual lifetime or the remaining lifetime or the excess lifetime at time t is given by the time from t to the next renewal epoch. So, the next renewal epoch, whenever t is in this particular interval, the next renewal epoch is at this point, right, s n plus n of t plus 1 minus t. So, this is what we called as the residual lifetime or excess lifetime or remaining lifetime, okay. And is also called forward recurrence time at t, like when you are looking in the forward in time, like what is the time that you have here. As opposed to this, the spent lifetime or the current lifetime or the age at time t is given by the time to t since the last renewal epoch, which is t to Sn minus 1. Okay. So, if I look at the diagram here, so basically this is my S of n of t and this is my S of n of t plus 1, and if I call this as t, then this quantity is what you call it Z of t and this is you call it as Y of t, right. So, that is what we are saying it here. Okay. So, this is also called age because this is what is happening, is also called backward recurrence time. The total lifetime or the length of lifetime that contains t is basically given by the sum of these two, which is nothing but your S n of t plus 1 minus S n of t, which is also equal to x of S n of t plus 1. You can think about this in the queuing context as well, right. Suppose if you are thinking about this arrival, same thing with service or any other event, but let us stick to arrivals here. So, if the events that we are talking about here are arrivals, that means there is an arrival here at this point, there is an arrival at this point. This is your current time. So, this Z of t would then denote that it is the elapsed time since last arrival, okay, and this is time to the next arrival from the current time point. Okay. Now, in Poisson process case or in Markovian queuing models case, when we associate this relationship for the time interval, the first one, the arrivals at any given point of time, because of this memoryless property, this distributions is that whether you are looking at Zt or Y of t, they are all simply exponentials, right. So, this mainly we will be interested about time for the next arrival. So, that will be exponential because of the memoryless property, right. So, that is the reason there you had, but here since it is exponential distribution is the only distribution that has the memoryless property. So, you do not expect when you assume a general distribution for inter-arrival times or service times, you do not expect that exponential property to hold here, right. So, we need to consider this exclusively if we are interested in say residual lifetime or excess lifetime and so on. So, this will play a critical role wherever, say for example, waiting time computation at whatever time it is you are arriving. Now, the time when the last customer arrived and time now, like in the earlier case what we did, you just counted in front of you how many customers are there, you just summed up them, all of them are basically exponential. Suppose if it is not, if it is service is happening with respect to a general distribution, then you have to compute the remaining service time for the customer who is currently in service, add up to the remaining ones who are waiting in the queue. So, you have to split that into this case. Now, to compute that you need the distribution of the remaining service time, which is basically this Y of t process. Okay. So, that is where the modification will come, and hence this is important in the analysis if we are using a renewal process as opposed to a Poisson process for arrival or service and so on. Okay. So, these random variables, that is what we said, it arise naturally in queuing context, say arrivals, departures, etc. Now, before we talk about its distribution, we define this notion of what is called as a random variable or its distribution function being lattice. What do we mean? A non-negative random variable and also its equivalently its CDF also can be said so is called lattice if there is a positive number d greater than 0 such that probability of x equal to nd equal to 1, and the largest such d such that this is true is called the period of x and also of f. Okay. So, it means that the mass, so there is a positive d strictly greater than 0 and the mass of this distribution is concentrated on the points ND for n0 to infinity. If you have such a random variable, this is what is called as a lattice distribution. Okay. Now, the distribution of yt, which is what is most important, it can be obtained as in this way. We are not going into the derivation, but it is not very difficult, but you need to capture an idea in order to write this expression. So, the distribution you can write in terms of the distribution of this xn and the renewal function. So, you need the renewal function here. Okay. So, this distribution of the remaining or residual lifetime is given as this, which requires your renewal function, right. And if f is non-lattice, then one can think about the limiting distribution of this yt, which we call it y less than or equal to x, or which is this quantity, which is probability of yt less than or equal to x as t tends to infinity, right. So, this is what we are looking at as as convergence in distribution sense, which is equal to this quantity. So, this is now becomes independent of the renewal function. You do not need renewal function. If you have f, then this is given by this. If you are interested only in the limiting distribution of this, okay, which is what is normally we would be interested to know, and that is given by 1 over mu, which is the rate of the renewal process, multiplied by 0 to x of 1 minus f of y dy is what the limiting distribution of the residual lifetime. And noting that the relationship between y and z, the distribution of z can be deduced to be equal to this, where again m is also involved, f is also involved, and is again, if f is non-lattice, then the limiting distribution of this zt is basically one can obtain it as again in this way. So, it is the same, right. So, that is what you get here. So, whenever this exists, of course, you can verify whether this is, if there is any issue with this, you can just verify anyway. So, the two limiting distributions are, when these exist, the two limiting distributions are identical. That is what we are seeing here, and it can be easily verified that for exponential xi's, the distributions of yt and zt are again exponential. That means here we are not talking about this, which is the limiting distribution, they are identical, but for exponential case even this will turn out to be the same with mean mu, which is expectation of xy. Now, from this one can also obtain, from this one can also obtain the mean of y and z, that is this quantity, because this is what is the distribution, because both have the identical distribution. So, the mean also is the same, which is basically given in terms of the first two moments of the intervals, renewal intervals, which is expectation of xi square divided over twice expectation of x. Okay. Now, if f is a lattice distribution, then here we are putting only for non-lattice. If it is lattice distribution and this have no limits for t to infinity except in some special cases. So, which we are not concerned about that at this point of time. That is what you have here. Now, some generalizations of this renewal process. Okay, so, let us look at here what is called first as delayed or modified renewal process. Okay. So, if we start with the process at time 0, if there is a renewal happens and then the process is continuing, then it is the ordinary renewal process, okay, which is the case. For example, if you have a tube light or bulb which you are installing for the first time, and then from then you are counting the time of its failure, right. The next renewal, so and so on, it goes on. Rather, if you are counting, for example, the bulb was installed at some point of time, you do not know when, but you are now starting your count at this point of time. So, the bulb was in operation for some time before, so you are starting at this point of time, the bulb will fail after some time. Okay. So, basically this, the first one then is not same as the subsequent ones, because this is not the point of renewal, this is point of not non-renewal, like the renewal happened sometime before which you don't know, you did not capture. So at this point of only you are observing. Okay. So so that means the first one alone, if you think about, has a different distribution, say G, which is different from the common distribution F, which is what you apply for the remaining inter-arrival times, which is inter-event time, which is x2, x3 and so on. Then what we get is a modified renewal process or delayed renewal process, because you are delaying renewal process until the first occurrence of this, after you start observing that. In between you are calling that as by some other G. Okay. So as we said, when G is equal to F, then the modified process reduces to ordinary renewal process. So typically ordinary renewal process is what is the word used for the most common case here. This is one. The other one is alternating renewal process. So this is basically a stochastic process with two states, 0 and 1. Suppose the process starts in state 1, which is called, you may call this an up state, and it stays there in that state x1 amount of time and then jumps to state 0, which is a down state. Okay. You can think of this as a working condition and failure condition and repair condition, failure condition, right. So it stays in this particular state 0 for y1 amount of time and then goes back to state 1, and then it stays there for an x2 amount of time and then it comes back to state 0, stays there for an y2 amount of time and then goes back and forth. Okay. So that is what is the scenario. So this is basically alternating renewal process is what we call it. So nth uptime will be powered by the nth downtime is what called the nth cycle. Okay. As an example, you can think of the lifetime or the time to failure given by the sequence xn of the IID random variables, on the assumption that detection of failure and repair or replacement of the failed component is instantaneous. Okay. Then you have only one working state, that is all you can think about. Now that is a normal renewal process, that is what you will have. Now instead, it is not that the replacement or the changing of bulb in the bulb example is not instantaneous. Okay. And but it will take some time, so which is what we call it as up and down. So there it takes some time, either you have to buy and replace it, or you have to repair that and put it, or whatever you want to do, it will take some time. Then you can have this alternating renewal process business. So when you have these failed items are not instantaneously replaced and it takes some time for it to bring it to up state. Okay. So then this process has two states, the working state and the repair state, and duration of the working states are given by a sequence of IID random variables, the duration of repair states are given by a sequence of IID random variables. Then we have an alternating renewal process or a two-stage renewal process is what this particular example that we can have here. Okay. So this is what all about renewal process that we want to get some idea about. Basically, what is the renewal process? How this is connected with other processes that we have seen earlier, right? Poisson process, which is a Markov process. Whenever you have this, the renewal intervals or IID exponential, it becomes a Markov process and Poisson process especially. So this is a generalization of that is what then we have considered. Okay. And then the additional notion which are required in the excess lifetime, mainly remaining lifetime or time for the next arrival in our context, or time for the service completion of the ongoing service, right, when you look at an arbitrary time is what this quantities are you have. Okay. So this is what one has to consider, and how we will consider and everything like that we will do it as we go along. Okay. So this is about renewal process. So the semi Markov process thing, like we will take it up in the next lecture. Okay. Thank you. Bye.